Hey guys, this question wants to know which of the following is a suitable reagent for a Friedel-Crafts alkylation reaction. Be very careful to note that it's an alkylation and not an acylation reaction. Okay, they're very different. Very quickly, let's review the mechanism for how that works. Basically, your chlorine from your alkyl chloride will interact with a Lewis acid in the form of AlCl3. In other words, this will attack that empty p orbital of the aluminum and form this kind of reactive intermediate, kind of looking like this, which creates a partial negative there and a partial positive over there, which is then released by doing this, and you get your positive there, which is then in turn attacked by the benzene ring. So this acts as, this becomes the electrophile, and then you do the benzene attacks it in what you definitely should know as the electrophilic aromatic substitution reactions. Okay, we won't go over that in this video because we're focusing just on sort of the reagents that we're using and why we can use some and not other. Okay, the important part here is you're forming this electrophile in the form of a carbocation. That's the key to a Friedel-Crafts alkylation. What does that mean? It means that typically you want to form something that is relatively stable. You want to form you want to choose the reagent that gives you your best carbocation. So if we look at A, in the Friedel-Crafts one we'd get a primary carbocation. That's the intermediate we'd get here, you see? And we know that primary carbocations are not very stable. So this Friedel-Crafts wouldn't work as well. Same goes for B. In fact, with B, you'd get this carbocation, and then probably what would happen is this would rearrange, and you'd get the secondary over there, right? Because secondary carbocations are way more stable than primary carbocations. If you are confused about why that is, go and just go onto YouTube and search for the term hyperconjugation. Hyperconjugation, and it'll explain to you exactly why a secondary carbocation is more stable than a primary, and a tertiary is more stable than a secondary, etc., etc. Okay. Let's look at C. With C, we again get a primary carbocation, and this time it's kind of even worse because now with the rearrangement, we'd get or with the hydride shift, you get a tertiary from the primary carbocation. So C is also out. So A, B, and C are all bad choices. D is the same issue as C. You're going to get a carbocation that is secondary, but with a rearrangement, you'll see a tertiary. So it basically means that, you'll have some of this, some of this, some of this, some of this, and the benzene will attack both, which will give you a mixture of products. And remember, when you're doing chemistry in the lab, you want to get as few products as possible, because when you do chemistry and you get lots of side products in your reaction, it's going to be very hard for you to purify the part that you want, and it lowers your yield. It basically makes it a poor reaction. Okay, so then finally we go to E, and that is that when that chlorine finally leaves, you get a tertiary carbocation, and you're not going to want to rearrange that to a primary at all. So now the benzene would attack that, and finally your product would be this Friedel-Crafts product, looking like this. Okay, so E would be a fantastic reagent to use in a Friedel-Crafts alkylation reaction. It's not necessarily the only one that would work, but it's the one that works the best and has the fewest rearrangements possible. So therefore, E is going to be our final answer choice here. Thanks for watching, guys. If you have any questions, shoot us an email, and we'd be happy to explain things in more detail. Have a nice day.